Welcome to Everyday Mathematics. Today we move forward to the MIT Integration B Qualifying Exam 2011, problems 11, 12, 13, 14, and 15, where problem 11 was the indefinite integral of cosine of natural logarithm of x. Problem 12 was also an indefinite integral of 1 over cosine x. Problem 13 was the indefinite integral of 1 over 9 cosine squared x plus 4 sine squared x. Problem 14, indefinite integral of 1 over x squared times open bracket x to the power 4 plus 1 to the power 3 over 4. Problem 15 happens to be a definite integral from x equals to 0 to x equals to pi of cosine x times cosine 3x times cosine 5x. So I hope we have some fun solving these problems. They look certainly very interesting, and I hope they do interest you as well. So on to problem number 11, the indefinite integral of cosine of a natural logarithm of x. So the interesting bit here is that I think we'd have to substitute for log x, and we say let u be equal to natural logarithm of x. And what that means is that when we differentiate the natural logarithm of x with respect to x, that is du dx, and then we get 1 over x. But before that, I think the important thing to see here is that the relationship e to the power u equals to x is also going to be vital for us. So that when we have du dx being equal to 1 over x, we can say that by multiplying with dx on both sides, that du can be substituted for dx over x. So now we pull back this expression that we have here, and so what we can do is we can add a phantom x here, or just an imaginary x, and there we have dx over x, and so this part here now is equivalent to, can be substituted away using du. And so again, we know what x is here. X is e to the power u, and natural logarithm of x is certainly going to be u. So now we do have the integral in the u domain. We've shifted from the x to the u domain, and so we have the integral of e to the power u cosine u. I'm going to try and employ what we call differentiation by integration by parts. And so e to the power u can be expressed as the derivative of e to the power u. E to the power is a very special function because the derivative of e to the power u or e to the power x is e to the power x. So we can express it this way, so that now when we look at our problem, we do have a very good candidate for integration by parts. What does integration by parts look like? Integration by parts tells us that if you have an integration of a product of two functions, whereby one function is considered to be v and the other one is a derivative of a function u du, then the integral of that function, the product of those two functions, is the same as euv minus the integral of u and the derivative of v. And this really comes from, if you have uv as a function you want to differentiate. That's the same as differentiating the product of u and the derivative of v, the sum of u and derivative of v, and the product of v and the derivative of u, so that when you integrate what you're differentiating, then reorganizing it, we get exactly what we're seeing here. So from here, we'll consider u to be e to the power u and v to be cosine u. So that what uv now becomes is eu, e to the power u, times cosine u, minus, now the product of u, e to the power u, and derivative of cosine, which is negative sine. So the negative and negative here can interact, so we have a positive plus the product will be the power u and sine u. And then you again do the second, the nested integration by parts, where we repeat the same exact process. And the reason we're doing this is because we want to go back to a point where we're integrating the product of EU and cosine U. So we've done one more level, and the blue here is what belongs to this second integral. So quickly we have seen that this here is the same as our original integral up here. And so we can dab that integral as I, and then this also can be I, so that when we collect like terms on the left hand side, we now have 2I, right? So we have 2I being equal to e to the power u cosine u plus e to the power u sine times sine u. And obviously there's an integration constant there that we'll add later, so that 1I is half of what we have on the right hand side, right? And so since we know that u is equal to natural logarithm of x, we can plug natural logarithm of x where we see u. And we know e to the power of natural logarithm of a number is the same as that number. This here, e to the power natural logarithm of x, is the same as x. And so we'll simplify it that now our integral here is half, open bracket, x cosine of natural logarithm of x plus x sine natural logarithm of x, plus the integration constant. Sorry, my cursor is choppy here. So this is our answer. This is what was expected. So if you have any question, regarding this problem, feel free to reach out to us. Problem number 12, very interesting problem, the definite integral of 1 over cosine x. In some circles, this would be the indefinite integral over secant of x. And this is a problem that can easily trip a lot of people. So what I usually do is I put secant x plus tan x both in the numerator and denominator, which essentially, would cancel each other, so it's the same as 1, but putting them there is very important because then that simplifies a lot of things. Because now when we multiply secant x across, then we have secant squared x plus secant x tan x. And what secant squared x is the derivative of the tangent of x. And the secant x tan x is the derivative of secant x. And what you're quickly seeing is that the numerator here is the derivative of tangent of x plus secant of x, or secant of x and tangent of x. So the numerator is the derivative of the denominator. And we know from, for those of you who are very familiar with integration, is that when you have an integral where we have the derivative of the function being the numerator and the function itself being the denominator, then the integration of that expression is the natural logarithm of fx plus c. So from here, our fx happens to be secant x plus tangent x, and that means that our integral of 1 over cosine x is a natural logarithm of, in bracket, secant x plus tangent of x, and then obviously plus the integration constant. And this is our answer, ladies and gentlemen. Well, again, if you have any questions in regard to this problem, feel free to reach out. There are other ways to try and manipulate these to get to a very intuitive way of reaching to natural log of secant x plus tangent x, but this was my shortcut, and yeah. This is a very interesting problem, problem number 13, the indefinite integral of 1 over 9 cosine x squared plus 4 sine x squared, or you could say the integral of 1 over cosine squared x plus 4 sine squared x. First thing I would do is I would divide both the numerator and denominator with cosine squared x. And so what happens here is we have secant squared x in the numerator and 9 plus 4 tangent squared x. Now if I pull 1 over 9 out, I have secant squared x over 1 plus 4 over 9 tangent squared x. And I would like to express this so that I could substitute away with whatever is inside the squared root here. So 1 over 9, the integral of secant squared x over 1 plus, in bracket, 2 over 3 tan x, all to the power 2. So I can substitute this with tangent theta. And that's what, in fact, I'm going to do. So I'll just say let 2 over 3 tangent x be equal to tan theta. So that 2 over 3 sec squared x dx d theta equals to sec squared theta. And what that means is I could substitute sec squared x dx with 3 over 2 sec squared theta d theta. And so now integral 1 over 9 of the integral of sec squared x over 1 plus 2 over 3 in bracket tan x all squared is the same as 1 over 9. In place of this part here, I'm going to put 3 over 2, this expression here, sec squared theta d theta. In place of this denominator here, part of the denominator, I'm going to put tan squared theta. So when I add these two components together, I get sec squared theta, and very soon we're going to see that we can now cancel the denominator and the numerator with the sec squared theta here and the sec squared theta in the denominator, because this part here is what leads to what we see in the denominator. And so obviously this is 3 and this goes by 1, and so in the denominator we have 3 times 2, which is 1 over 6 d theta, and that is 1 over 6 theta plus c. But you remember we said 2 over 3 tangent x equals to tangent theta. So theta is the arctangent of 2 over 3 tangent of x. So we can pull this entire thing and put it in place of theta there. So we have 1 over 6 arctangent of 2 over 3 tangent x plus the integration constant c. And that is, ladies and gentlemen, the answer that I think was required of us. So ladies and gentlemen, we now jump onto problem number 14, which is the integral of 1 over x squared times x to the power 4 plus 1 to the power 3 over 4. It's a very interesting problem. When I have fractions in the denominator like this, I know this kind of begins with the differentiation of whatever we have here. So what I do is when I look at x to the power 4, when I differentiate it, it doesn't really give me what I have here. So what I do is I remove x to the power 4 out, and so 1 over 4 to the power x to the power 4 to the power 1 over 4 is x, the x times to the power 3 is x to the power 3, then multiply by x to the power 2 here. So we've pulled out x to the power 3, and so that's the same as dividing by x to the power 4 inside the bracket here. And this becomes 1 over x to the power 5 times 1 over 1 plus x, 1 plus 1 over x to the power 4, the power 3 over 4. Now, clearly I see that 1 over, because there is a hidden 1 up there, 1 over x to the power 5 is the derivative of the negative of the derivative of this part here, which now makes me enjoy this. This is very interesting. So I want to substitute for 1 over x to the power 4. So let u be equal to 1 over x to the power 4, and so the derivative of u with respect to x is negative 1 over x to the power 5. For quickly, I've seen that I could easily substitute 1 over x to the power 5 with what we have there. But let's just continue. So negative du can be used to substitute dx over x to the power 5. So essentially this part here can be substituted off, right? And so our integral now becomes the integral of 1 over 1 plus u with the negative, and this, the integrand here can easily be seen to be this when you integrate. So plus 1, because it's negative 3 over 4, plus 1 becomes 1 over 4, and obviously when you differentiate this part here, there is a constant 1 over 4, so to negate that constant we've put 4 here. So negative 1 over 4 times 1 plus u to the power 1 over 4 plus c. Now we know what u is, since we said u be equal to 1 over x to the power 4, so we can plug in place of u 1 over x to the power 4. And so this is the answer that was asked of us. So if you have any question, please feel free to reach out. Then problem number 15, which is a definite integral or from x equals to 0 to x equals to pi of cosine x times 3x times cosine 5x, cosine 3x times cosine 5x. So this is just a product thing, and I would like to begin with my identities. When you have cosine a plus cosine a minus b, the same as cosine a cosine b plus sine a sine b, and cosine a plus b is the same as cosine a cosine b plus sine a sine b, so that when you add both the left and right hand sides of that, we find that cosine a minus b plus cosine a plus b is equals to twice cosine a cosine b, and cosine a cosine b is the same as half of open bracket cosine a minus b plus cosine a plus b. And so if a, b, let's say for example, if we focus on this first part here, right, and if a is maybe 5x and b is 3x, then we can now say our integral here is the same as cosine, the integral from x equals 0 to pi of cosine x times half cosine of 5x minus 3x, which is cosine 2x, plus cosine of a plus b, which is 5x plus 3x, which is cosine 8x. And so when we multiply through, we pull half out, so we have cosine x times cosine 2x as the integrand plus cosine x times cosine 9x. Again, you repeat the same process where a is 2x and b is x here, and here a be 8x and b be cosine x. So we repeat that process, so you have two subintegrals here, and we have integral from x equals 0 to x equals to pi of half. A is a minus b is 2x minus x, which is x. A plus b is 2x plus x, which is 3x. Here, a minus b, a being 8x, 8x minus x is 7x, 8x plus x is 9x. So, and then we can pull out those two halves there, so that we have a quarter of cosine x plus cosine 3x plus integral from x equals 0 to pi of cosine x plus cosine 3x plus cosine 7x plus cosine 9x. I mean, from here already you can see it's 0 because all these functions are periodic, and since you are moving from you're moving from a positive all the way to the negative, so you have the positive law cancelling out the negative law. But I mean, let's not really dwell into the analytical part of it and just say, okay, if you integrate the things, what you get is sine x plus 1 over 3 sine 3x, and then you have 1 over 7 sine 7x plus 1 over 9 sine 9x. And as you can see, both at the upper and the lower limit, sorry, this is pi, this is not 2, that's a typo. But when we substitute pi in all these functions, it becomes 0. And at the same time, when we substitute 0 into all this, we get 0. So essentially, the answer is 0. I mean, it's very easy to have seen this high up there, but I think it's cool to do it until everything seems clear. So that brings us to the end of today's set of problems. I hope you had some fun following through. If you have any questions, please feel free to leave them in the comment section. We really love to interact with you, and I would love to also share your versions of the solutions to some of these problems. Until next time, à tout à l'heure, à la prochaine fois.